Ready? All right, everyone. Welcome. It's Wednesday, first Wednesday of the month. Welcome to another episode of Talking Trout. I'm Mike Coor. I'm the former state council chair for Wisconsin Trout Unlimited. I was, glad you're able to join us tonight. We got a pretty interesting guest, Brandon Thill, and he's joined by Professor Jason Freund. Brandon's a graduate student at UW-La Crosse, and he's been doing some really interesting research on brook trout habitat versus, brook trout streams versus brown trout streams in the Driftless area. And we thought it would be a topic that would be of interest to folks in the Trout Unlimited community here in Wisconsin. And so we're happy to have you, Brandon. Again, folks, if you got questions during the presentation, by all means, drop them in the chat box. We'll get to them at the end of the evening. And Brandon, grew up in Wisconsin. I think he grew up in the Madison area, if I have that right. And he's been doing some, like you said, he's been doing some work at the school out there, UW-La Crosse, and so we're glad to have you, Brandon. I'm going to turn it over to you and give you the floor.
Yeah, thanks, Mike. So as mentioned, my name is Brandon. I'm a grad student at UW-La Crosse, going on my 4th semester in grad school, and I just want to say thanks for having me here, and I'm excited to share what we've been working on, which is brook trout. More specifically, suitable habitat for brook trout in the Driftless area here within 2 different rock geologies, and that's sandstone and dolostone. So, 1 second. To start things off today, just a brief outline of kind of what we'll be covering. I'll start with an introduction to brook trout and a little bit of our study area, move into the objectives of my research here, look at some temperature data, some habitat modeling stuff, and then I'll wrap it up with a little conclusion. But to talk about brook trout, we got to learn about brook trout. And I'm sure most of us are pretty familiar with the species. They are the only stream trout native to Wisconsin, but now they're living in and amongst brown trout, possibly rainbow trout, and they're known as cold water specialists. So brook trout do best in colder water. They need it to thrive and to grow successfully and to reproduce. Those brook trout eggs need cold, fast-flowing water to successfully hatch. And when the fry or the young trout emerge from those eggs, they need cold water as well in order to grow. And it reduces the chance of them developing something like a deformity. So being cold water specialists, brook trout have what's called a thermal preference and a thermal max. So that preference is sitting around 22 degrees Celsius. And as stream temperatures may begin to rise and get towards that 22 degrees Celsius mark, some stressors might start to take place on the brook trout. And essentially, they're not going to want to be there anymore. But once we get to that thermal max around 25, then we start talking about major stressors and possibly even things like mortality occurring within populations. So the state of Wisconsin around 2019 was expected to look something like this, where these green areas represent suitable habitat or places where brook trout could live. Now this percentage of habitat in the state is expected to decrease 68% by the year 2050. And that's a pretty big percentage. And the state of Wisconsin would therefore look something like this. Now I want to draw your attention to this map on the right, and more specifically this area within that purple box. And there's the city of La Crosse for reference. So the question kind of becomes, why is this green spot here? What allows these streams in this area to remain healthy and suitable for brook trout when now surrounded by all of this red and yellow and orange? Well, there's a couple factors that can play a role in a decline that we see like this. We have abiotic factors, or more environmentally based things. And we have biotic factors, or dealing with other organisms. Some biotic factors include competition in and amongst species of fish, predation by other fish or maybe terrestrial organisms, insect declines or a decline in food resources or food availability, parasites like these gill lice, which inhabit the gills of the brook trout, ultimately suffocating them and causing them to die, and infertile reproduction like this tiger trout here, which in itself is not able to reproduce and pass on genes. So before moving on to those abiotic variables or factors, I want to introduce the brown trout. Now, the brown trout is very, very important in this whole study because they're responsible for multiple factors on this list here to the left. By far, the biggest competition for brook trout is a brown trout. They can outcompete them for food resources and positions within the stream, like resting spots, feeding spots, and even hiding spots. Brown trout eat brook trout. Now, I'm not saying that brook trout don't eat brook trout. I actually witnessed it, but we'll talk about that later. But when you add brown trout to the equation, more brook trout are being eaten. And infertile reproduction, such as that tiger trout. So that's the result of a cross between a brown trout and a brook trout. And as I mentioned, that fish can no longer reproduce. Continuing with brown trout for a little bit, they are not native to Wisconsin. And as I mentioned, the biggest competition for brook trout. They also have higher thermal max preferences and limits. So as the streams may begin to get a little warmer, the brown trout, they have an easier time persisting in those streams if they're present, therefore aiding in their ability to outcompete the brook trout and possibly push them out of the water. Back to those abiotic factors, we got things like climate change, temperature variability, stream connectivity, and habitat degradation. Now, each of these things are very important in themselves, but when paired together, can really amplify the effects on a stream and the inhabitants within it. So as our climate begins to change and our temperatures become more variable, our stream temperatures are going to rise. And as they rise, they might start to approach or pass those preferences and limits that I had mentioned, therefore causing stress on the brook trout. Stream connectivity and habitat degradation become an issue when populations of brook trout become separated. And those disjunct populations of brook trout are then more succumb to things like a lack of genetic diversity and even inbreeding, both of which can be detrimental to that population in itself. So to focus in on our study area here, or where we did this research in the summer of 2023, we've seen this map on the left. And I have now placed a black box, which encompasses the study area. And we can see within that black box is the green spot that I had talked about. Now, the map on the right is a bedrock geologic map of Wisconsin. And what it's doing is showing us the underlying bedrocks within the state. So zooming in on that map and our study area, the one thing that sticks out right away is this pretty clear divide between our yellow sandstone to the north and our blue dolostone to the south. And what we have observed is that our brook trout are more typically residing in that sandstone area, whereas the blue dolostone to the south is much more dominated by brown trout. Another important thing to consider about these two regions and the streams within them is how the water is entering the streams. So our sandstone dominated streams had much more of an input from groundwater. So that water is able to enter the stream throughout the whole stream bed, therefore making it a more constant, colder environment. Whereas the dolostone region is more dominated by springs. Now, springs are a nice input of cold water, but it's more concentrated to 1, 2, maybe several springs within the stream, but more spread out. So here's a map of all of our study sites. There are 20 in total. The orange star here is the city of La Crosse. And for those of you familiar with the area, we have a few more popular streams in the south, like Rulin's Coulee, Timber Coulee, and Coon Creek. And to the north, we have streams like Big Creek, Burns Creek, and Rathbone Creek. But I want to kind of touch on these two streams side by side. There's a few differences we can see right off the bat. And the first one I want to talk about is the substrate, or the composition of the stream bed. Our dolostone streams are primarily cobble, gravel, and heavy macrophytes, or lots of weeds in these streams. Whereas we look to the right in our sandstone streams, it's a lot of sand, hence the name, and less macrophytes, or less weeds in the stream bed. The next thing I want to point out here is the riparian areas around the stream. Our dolostone streams were typically much more open and didn't have many trees or shrubs surrounding the stream, whereas in this picture of our sandstone stream, we have high canopies of trees and shrubs. Ultimately, what this is doing for those sandstone streams is providing more shade and keeping them a bit cooler. And the last thing I want to point out, and it's hard to see from these two pictures, is the lack of channel units that we witnessed in the sandstone streams we sampled. So the majority of them were one long run, or relatively deep, relatively slow moving water. Whereas in the dolostone streams, we had that presence of pool, riffle, run complexes that we might be a little more used to. But we'll talk about these as we get into the results. Looking into the streams more individually, our sandstone streams had a little bit lower productivity, were a little less basic, and the average sandstone watershed had 61% forest cover and 30% agricultural cover. We can compare that to our dolostone streams, which had higher productivity. They had that harder, rockier stream bottom and that presence of cobble and gravel. And the watersheds had a little bit less forest cover and quite a bit higher percentage of agricultural cover, sitting around 53%. So we talk about land coverage and trees and agriculture, and that pairs with soil infiltration rates. So I've used a program called Model My Watershed and taken the average percent coverage of different infiltrations of soils within our watersheds. So what I really want to focus on here is that red bar at the top, and that's our high infiltration soil. We can see that the sandstone watershed is far more dominated by that high infiltration soil, that sandier soil. So what this means is that water coming from an outside source has an easier time infiltrating the surface and percolating down through the soil into the groundwater. Looking over to the right at the dolostone watershed, we see a lot more moderate and slow infiltration soil. So that water is having a harder time getting down into the groundwater storage. And we can then pair that with that added agriculture. So with more agriculture, we essentially have more nutrients. And with a harder time for the water to enter the soil and infiltrate the surface, one could hypothesize that it has an easier time running off directly into the stream. So this could be paired in our dolostone watersheds with excess nutrients entering the stream. So to talk about my objectives for my research as a whole, we had 3 of them. The first, to quantify brook and brown trout habitat in Monroe and Vernon counties. The second, to assess the influence of geology, land use, and that soil composition. And third, to determine which variables in our streams have the strongest correlation to summer stream temperatures. So temperature is really big, as we've talked about, when it comes to brook trout, and well, all trout. And as we know, last summer was hot and it was dry. And this can have really damaging effects on the stream's health itself and the inhabitants within it. It can raise water temps, increase vegetation growth, and even lower water levels. And temperature affects fish both directly and indirectly by changing their rates of metabolism, changing or affecting their willingness to feed and their overall ability to grow. Indirectly, temperature affects prey availability, so it can lower the amount of prey available for these fish to eat. It can also mediate competitive interactions. So as that water, that stream water might be getting a little warmer, maybe that threshold of 22 degrees is getting close or getting past, those brown trout are then able to do a little better and possibly outcompete those brook trout. So what we did to measure this is place temperature loggers in 11 streams, and they were set to record every 15 minutes from the months of July through August. And here's what that kind of looked like. So this figure here is showing water temperatures for each of our highest discharge streams, or each of our biggest streams, in the dolostone and sandstone regions. So our dolostone is going to be in the orange, that top line, and the sandstone is the blue, or that bottom line. What we can see right away here is we hardly have any overlap between our sandstone and dolostone streams. So ultimately, that sandstone stream is remaining colder than the dolostone. And what I can do is add that 22-degree threshold and that 25-degree max limit. And now it becomes really apparent how often that dolostone stream approaches, if not crosses, that 22-degree preference limit of the brook trout. And even looking into late August there, when we had, I don't know, 106 degrees or something, that dolostone stream just about got to that max limit for the brook trout. Now, I want to put air temperature on top of this just to kind of highlight how it plays such a big role in the stream temperatures. We can see a pretty constant measure when it comes to the warming of the stream during the day and the warming of the air during the day, as well as the cooling of the stream during the night and the cooling of the air during the night. This figure here, we can see something a little different. And these two lines are each of our lowest discharge or smallest streams within the dolostone and sandstone region. Again, our dolostone's in the orange and our sandstone is the blue. But what sticks out here is that ultimately the dolostone stream is getting warmer and cooler than the sandstone stream. Now, this variability in itself can cause stress on a fish. Whereas in our sandstone stream, the environment is relatively constant, providing more stable environment and allowing them to live a little bit less stress-free, more stress-free, sorry. I can also add that 22 and 25-degree limit back on there. And again, just how often that dolostone stream approaches, if not crosses, that preference limit becomes very apparent here. So aside from temperature, we looked at habitat modeling. And essentially, this is giving us variables within the stream that may or may not relate to the temperature. So as I mentioned, we had 20 streams in total. And at each stream, we needed a stream reach, or a length of stream that we were to measure. Now, the stream reach was defined as 30 times the mean stream width, or the average width of the stream. So if my stream was on average 5 meters wide, my stream reach would be 150 meters long. And I'll continue with this 150 meter long example here. So each stream reach was divided into 31 transects. And each transect was spaced 1 mean stream width apart. So for my 150-meter long stream reach, I had transects spaced 5 meters apart. Now at each transect, we measured at 4 points, and that was the middle, the left, the right, and the Thalweg point. So the Thalweg is typically known as the fastest flowing, deepest part of the stream, and it's variable. So it could have been here. It could have been all the way over here on the right or all the way over here on the left. It was different at each transect. So at each of these points, we measured 8 variables, and those variables included stream depth, average current velocity, bottom current velocity, distance to cover, type of cover, if riparian shade was of influence or not, if that point was embedded, and the overall substrate composition of that point. So to kind of visualize this, I've added these pictures, and on the left is our reach tape. So that's that 150-meter long measuring tape, which we use to measure out our transects. And on the right, we have our transect tape going perpendicular to the stream, which we used to measure out the left, middle, and right points. So for each stream reach and all 31 transects at each reach and all 4 points at each transect and all 8 variables at each point, we would end up with something that looked like this and this and this and this. Now, this is an overwhelming amount of data, and that's the point. It is so much data that we have to work with. But what it can do for us is tell us what habitats are available in these brook trout dominated versus brown trout dominated streams. We can now numerically paint a picture of the bottom of the stream and kind of pick out how these variables are maybe influencing the temperature of the stream as a whole. So getting to some results here, we'll start with depth. So our dolostone on the left and sandstone on the right, we can see that on average, our sandstone streams were a little deeper. And one could hypothesize that this is because of that lack of channel units that I'd mentioned before. So we're not seeing those shallow riffles that we see in the dolostone streams. Looking at current velocities, here our dolostone streams tended to be a little faster moving water. Again, you could maybe pair that with the added riffles, which are shallow and fast moving. Whereas in our sandstone streams, it was pretty much just one long run. Looking at substrate compositions, this really just drives home the point that our sandstone streams were a lot of sand. The majority, around 58 to 60% on average, was made, the bottom of the sandstone stream was sand, where our dolostone streams were more typically that cobble and gravel. However, if we look at boulder, silt, and debris, they did remain relatively similar between both of these regions. So now getting into more of the nitty-gritty stuff, this here's a correlation matrix. And what it's doing for us is giving a list of variables, which is the same on the side and the top there, and telling us how they correlate or relate to each other. So darker blue colors mean a more positive correlation, whereas darker red colors are going to be a more negative correlation. Now, this is a lot to look at, but I want to draw your attention to the relationship between mean temperature and basin area. So typically, we tend to think bigger stream, maybe bigger temperature, or warmer temperature. Excuse me, and smaller stream, maybe smaller temperature, cooler temperatures. But what we're seeing here is that's not really the case. We have a slightly negative correlation, close to 0. And it's telling us that size of the stream is not really influencing the temperature of the stream, which is pretty cool and will become important. I've also ran some AIC models, and this one here is with a response variable of mean stream temperature. Now, what this model is doing for us is telling us the weights or the influence of variables that play a role in the temperature, the mean temperature of the stream. So as mean temperature for a response variable, there were three main other variables that stuck out here. And that was mean depth, geology type, and conductivity. So geology type in this scenario was classified as a 0 for sandstone or a 1 for dolostone. And overall, our sandstone streams were deeper and had lower conductivities. So mean temperature was lower in our sandstone streams. This AIC model is dealing with mean temperature range. So the warmest time of day for the stream and the coldest time of day. And we see something a little different here. We have embeddedness and conductivity being the most influential on this mean temperature range. And what we've seen in that figure I had showed you is that our sandstone streams have a smaller range of temperatures throughout the day. And they tended to be more embedded and have lower conductivities. Lastly is this principal component analysis. And what we're looking at here is on the PC1 axis, or the the x-axis, we have a difference in geology type. And we're seeing negative relations between things like percent forest and percent high infiltration soil, and percent big rock and percent gravel, along with conductivity back there. So it's placing our streams on this axis where our sandstone streams are more over to the left and our dolostone to the right. Our PC2 axis, or the y-axis, is showing a difference in stream size. And we have negative relations between things like percentage of the stream that's shaded and distance to cover, as well as depth, basin area, and current velocity. So taking a step away from the habitat modeling, I also swam in some snorkel surveys. And what this allowed me to do was pick out in-stream fish position data and how fish are using specific habitats within the stream itself. So I swam along in the stream looking for fish doing one of two things, and that was either resting or feeding. And fish were deemed resting if they were on the bottom, and feeding if they were suspended. Now, once I found a fish, I would place a bright orange spray painted rock in this top picture in the location that I found the fish. At that location, we would then take those same habitat variables that we used for the habitat modeling for that specific location. And what it's going to allow us to do is say, what makes that spot so special for a fish that wants to feed or a fish that wants to rest? So here I've provided a video of what it looks like in the stream. And this isn't my video, but this really is what it looks like. You can get this close to the fish. And I would deem these fish to be feeding, as you can see from the one that just rose there. And if we encountered a group or a school of fish like this, what would happen is I would pick out the biggest of the fish, place the rock there, and that would be the metrics for that school of fish. And this was super, super cool. I mentioned that I saw a brook trout eat another brook trout, and it's just something I'll never forget. But some takeaways here. Brook trout habitat is declining in our state. And this is due to things like climate change and competitive interactions. But habitat modeling is allowing us to see the bigger picture. Cool water temperatures are essential for brook trout. They need them to thrive and to survive. And there are several variables that are playing quite a big role in the temperatures that we have observed. But through things like conservation maps and even brook trout reserves, we can identify places and habitats of ecological importance to help conserve and protect this species for generations to come. And that's about it. Thank you.
Awesome. That was very interesting, Brandon. I appreciate that. Um, Boy, my mind's going now. You got me thinking. I gotta start by asking you to maybe just talk a minute about the snorkeling aspect of things, if you don't mind.
Sure. Let me.
It had to be such a cool experience just to go down there and just to have that experience like in the water with the fish. Like, how did they react to you? Like, talk a little bit about what you experienced.
Yeah, it was a really, really cool experience. I would get down into the water, and once your eyes go below the surface, you're in a whole new world. Um, the fish, I had chances to touch multiple fish. They didn't seem to mind as you swim up behind them. Whereas for us trout fishermen here, if you were to walk up on the bank, those fish would be long gone, and it's incredible. Um, there were times where I had to leave the stream because my dry suit had a hole in the neck, so constant cold water down into the suit uh, made it a little tough, but it was an extremely cool experience.
So you literally just they would let you swim right up behind them, huh?
Yeah, I actually, so
And they
we took,
wouldn't spook.
oh,
I mean, you can move slow and stealthy and just interesting. That's
yeah,
cool.
part of it was estimating the length of fish that I found. And what I did is carry a 12-inch dowel with me. And I would swim up and I could take the dowel and place it right next to the fish and get a pretty good estimate of how big it was.
That is great. Love it. Um, yeah, we'll be, super interested to see as you continue to dig through. It looked like you gathered quite a bit of data. It'll be interesting to see what comes of that for sure. Now let me ask you this: Are we taking a snapshot in time? Do you think this is something that needs to be like? Do you need to go out and collect the data next summer or the summer after that, or do you think the 2 or 3 month period that you were out there collecting the data, like the streams probably don't change if the idea, I guess maybe I'm answering my own question, if the idea is to compare a sandstone stream to a dolostone stream, or limestone stream or whatever, like maybe they don't change that much year to year, so that wouldn't affect the outcome of what you're trying to get. Is that true?
Um, in part, yes, but I think one of the big things that we actually got really lucky with this past summer is that we had very little rain, and it was very hot and dry. So being that although it's not the most typical summer, I would say it wouldn't hurt to do something like this where we do have a summer with more precipitation events, um, and maybe cooler temperatures might play a role as well.
Yeah, it'd be interesting, like, if you had high water, would the fish still be holding in the same spots, right? Or, if there's stronger current in those spots, you would think that they'd be looking for the places where there's less current, as probably their primary holding spots. So they probably would move a little bit throughout the system. But we'll leave that for you guys to go out and investigate in the future. There were a couple of questions that popped up in the chat, so I thought maybe we'd just roll through them here. David had a question about beaver dams. I know Matt Mitro is doing a big study on beaver dams right now. It's probably about 2/3 of the way through, I think, on a number of trout streams. But David's question was, do you think beaver dams will be a positive influence on the sandstone streams due to the high infiltration of the surrounding soils?
Um, I I don't think beaver dams would necessarily be beneficial to the trout, by causing these bigger pools and slowing the water. I think that it would have an easier time increasing the temperatures of the water in that spot. However, I can see where you're coming from, where with the constant groundwater coming up, it could create maybe a large, relatively cool pool for them to take refuge in. So I can kind of see both sides to beaver dams on these sandstone streams.
Yeah, that's interesting. Yeah, yeah, it'd almost be like when you think about, I don't know if you're spending time in Northeast Wisconsin, but there's a number of, like, around the Anago area, there's a number of spring ponds. It would almost be like that effect, right? If the beaver happened to build the dam like right, where this groundwater infiltration is sort of surging in, where these little seeps are, you've got this constant cold pool right there. It'd be interesting. But like you said, if it's not right there and it's getting silted in, it just gets shallow and they abandon it a year later, and then and then you've got all this silt, and that could certainly warm up in a hurry. So John had a question about dissolved oxygen. Is that something that you measured as part of your data set to compare between the two streams?
Yeah, so we did do water quality for all of our sites. Um, Dissolved oxygen wasn't very significantly different between both our regions, sandstone and dolostone. So for that reason, it wasn't really included in any of our analyses. But we did measure it, yes.
Okay, yeah, that makes sense. I think I had a question about one of your slides. You used the term embeddedness. Could you go back and maybe just reiterate what that means for us?
Yeah, so when we measured if the point in the stream was embedded or not, and we had a stick that the flow reader was on, and if that stick was to easily sink or penetrate the bottom of the stream, meaning if there was a bunch of silt or soft sand, it would be considered embedded. And that embeddedness in part plays a role with the velocity of the water at the bottom of the stream. So faster moving water is typically going to have not as much embedded influence, because that soft material can easily be pushed away with the water there.
Okay, interesting. Yeah, that's good to know. Okay. Let's see here. Travis had a question. Were these strictly either or dolostone or sandstone dominated streams? Says I asked because some consist of sandstone and dolostone layered basins. Did you specifically pick out certain streams that you knew were completely distinct, or did you have some streams that maybe had some crossover between the two types?
We definitely had crossover. There was a pocket in the middle in Coles Valley, and it's just south of the interstate running through Monroe County, where the majority of the stream was made up of sand. However, it had dolostone characteristics, such as the conductivity was high, as the dolostone streams were. and a much higher presence of rock within those streams. So we consider those to be our intermediate streams, whereas we also had streams to the extreme north sandstone and south dolostone.
Okay, interesting. Do you have any situations where like maybe you've had like the main river was like a dolostone stream, but it had maybe like sandstone streams feeding into it as like a tributary? I don't know. I guess I'm not a geology major, so maybe that stuff doesn't happen on the landscape. But is that a possibility that you mix like that as well?
Um, as far as it being the bedrock that would make it sandstone tributary and dolostone main stem, I'm not sure that we would come across something like that, but I can definitely see, and we actually didn't have any of these, but a more rock dominated dolostone main stem with tributaries primarily sand based substrates. But we didn't have any dolostone streams with other tributaries like that coming into them. No.
Okay. Yeah, interesting. Thomas was kind of making or just kind of making that connection. We oftentimes think like, especially with brook trout, like you said, they're super temperature sensitive. It hits like a certain temperature and they go looking for colder water. And it kind of makes sense if they're in a dolostone stream and there's an opportunity where like if there's a cooler sandstone feeder like coming into it, that'd be an easy place for them to scoot into for the summer. So
Definitely, definitely.
interesting things to think about. So let me ask you this: where are we going with? I mean, you're a grad student. You're doing some pretty interesting research here. Where do you think this is headed? And do you have like plans to publish? You gonna like write a paper? Or, like, what do you hope to be the end result of this research?
Yeah, I definitely plan to write it all down and get it out there. Uh, we're kind of in the beginning midst of that at the moment, as we're still working through some of the data, and I have to manipulate all of that snorkel data. But another thing we've talked about is creating some sort of map, highlighting maybe streams that share characteristics with those that we have found brook trout doing well in currently. So picking out streams with some of the same characteristics and placing those on a map that can hopefully be shared, and then those streams could be taken into account for maybe brook trout reserves.
Yeah, I was kind of thinking the same thing. That's immediately popped in my mind. And the DNR, we know, is in the process of rolling out that plan. Like you said, they've identified brook trout reserves, which I would assume. Like I said, I couldn't tell the streams that you were in were those brook trout reserve waters. Do you know offhand?
Yeah. So actually, a couple of those northern Monroe County streams are proposed reserve waters. Yeah.
Sure. Yep. Yeah, that would make sense. Yeah, and that's really interesting that it's such an interesting question that you set out to answer, right? Like why, right? You just there's this one little pocket in the Driftless when you run all the models and like everything else turns to brown trout water, like but this little pocket, I mean, it still looks like it's habitable for brook trout, and I just love the idea that you guys asked the question and just got curious and went out there and like tried to figure out the answers, and it sounds like you're well on your way to having some answers and having some data to back it up, which is pretty amazing. Great stuff. So let's see.
Yeah.
Do you have
Even
other? Go ahead.
just visually, these two areas are so different. We travel to this northern Monroe County. It's like a Northwoods kind of feel. There's many more pine trees and the sand and everything. Whereas in the Dolostone, it's a lot more of that farmland and oaks. So even just to the eye, without even looking at the stream, they're very different environments, and it's really cool.
Sure. Yeah. Yeah. And you said the sandstone streams, they tend to be less gradient, maybe less that they don't have like the riffles, or it's, you said it's almost more like a, a long straight run, huh?
Yeah, I, I'm not sure we saw a riffle in any of those northern Monroe streams, if any gravel at all. We did have streams 100% sand.
Wow.
Um, but another thing about them is they have tons of overhead cover, and the number of brook trout in those streams compared to say Seas Branch or Mapledale, those restoration sites, is so different. We did some sampling with the Wisconsin DNR, and in Rathbone Creek, for example, is a northern Monroe stream. We shocked for 250 meters or so and only got 22, 24 fish. But the amount of cover there could have easily should have been way more brook trout in there.
That's interesting. I wonder if, well, sometimes it depends. Well, I will say this: I did some brook trout, or, well, not brook trout shocking. We were mostly shocking brown trout in a smaller stream with the DNR. Was helping out with a project this fall, and what we found was in the Driftless in Richland County, and we're trying to pull as many brown trout out of the brook trout stream as we could and relocate the browns downstream. But what we found is we were shocking. The DNR had their backpack shockers, and we were kind of the volunteers helping with the buckets and the nets in the back, just collecting fish. But we would find they'd push those fish upstream, and then they would hit like a pool area, and like with like a big, almost like a plunge pool area, and it was a place where you could congregate, and then you would pick up all the fish for like that stretch. Like they just kept going upstream of us, until they couldn't get upstream any further. They kind of got to a spot and they didn't want to go through super skinny water, and so they just kind of sat there, and then you could catch them all. But if the streams didn't have that situation, like you were saying, it's quite possible that you guys were spooking fish out there, right? As you're walking through the stream, and there was just nothing. There was nothing to stop them from just keep going upstream. So that might be, and somebody from the DNR who does this on a regular basis, professionally, might have a different answer than that. But just as a general observation, who's somebody, from somebody who spent 2 days in the field doing it, that's definitely what we found. Is like we would push fish upstream, and then they'd hit a certain spot where they didn't want to go through skinny water, shallow water, and then you would just collect a pile of them. But
Yeah.
yeah, definitely interesting there. So Jack had a question here. Let's see. He said, did you observe from your snorkeling a difference in the distribution of trout in these stream reaches due to cold water infiltration? Yeah, did you, especially brook trout? So I'm trying to think of what exactly he's asking there. A difference in the distribution of trout. Do you find maybe are the brook trout huddled together, the brown trout spaced out, or vice versa? Or did it seem rather random throughout the stream?
Yeah. So I guess I wasn't really aware of where water was entering the streams, if there was like a specific point. But I did observe sometimes schools of 20 and 30 brook trout all in one spot, whereas other streams, they were more distributed throughout, maybe one over there, one over there, one over there. So yeah, I'm sure that could have been part of it. seeing that schooling like that in some of those streams. Uh, but also they were schooled in deeper pools, which could have been a place where water's entering the stream. Yeah.
Sure. Yeah. I remember I was fishing a brook trout stream with a friend last summer in the Driftless, and we came around the bend, and the brook trout were not facing upstream like you'd think they would be. They were turned almost 90 degrees in the stream, maybe not quite 90, but probably 75 degrees. And there were 20 of them that all had their heads pointing towards the bank in the stream. And I'm sure that there had to have been a seep or a little spring or something that was pushing water, cold water coming right out of that spot. And it was enough where there couldn't have been, there probably wasn't enough current to make it real difficult to sit where they were at. But it was just such an odd thing to come across in the stream because you're so used to seeing them, facing upstream. And here these all were like turned to the side. It was interesting, but they didn't want to eat. They were interested. They were just holding. They were hunkered down. They were not in feeding mode, that's for sure. But yeah, it was interesting. That'd be. Did you take video while you were out snorkeling? Did you get or like photos, or did you try to, or were you just placing rocks and gathering data? Or
Um, I did have a brief thought of maybe trying to get my hands on a GoPro or something, but uh, I wasn't able to get any of my own video. That
okay,
video I showed was from Kirk Olson, the lacrosse fisheries biologist who actually did some snorkeling himself. But yeah, that's exactly what I saw.
yeah, interesting. Yeah, that's cool. That's cool. I'd love to see more of that. It really gives you a real an appreciation for what those fish are dealing with on a daily basis. Just when you see that, like trying to sit in your lane and like you've got all this stuff just coming at you, and like just their ability to pick out what a piece of food is or not a piece of food is, or sometimes they're just trying it out. They're not even sure, right? And you just go grab this and then you put it in your mouth and then you decide whether that's food or not. And yeah, it's an amazing way to live. And for a species that's been on this planet for however many probably millennia, it's pretty awesome to see it up close like that and to be able to immerse ourselves. We're so focused on above the water, and like just to be able to have that experience to kind of flip it around and observe from below, that'd be pretty neat. So are you an angler? Are you I saw a picture of you and a pretty nice brown trout, right? Actually, a couple of them. So, do you angle as well? You fisherman?
Oh yeah, I love to be
Yeah,
out there.
yeah, cool, cool. Do you have any? Do you think you've gained any insights from doing this that you will apply to your fishing?
110%. I I have been in the stream and seen which rocks they're behind and what banks they're under. And those are things that I now look for uh, as I'm fishing, and it has paid off. It has. Um, yeah, they're very opportunistic feeders. I think so. I mentioned I saw that brook trout eat. It was another 1 or 2 inch brook trout, but I think what happened is I did spook that smaller one, and it swam right past that big brook trout, and he T-boned it, and just to be able to see that was super cool.
Yeah, yeah, that's awesome. Yeah, very cool. I know I've seen some pictures of some friends. Usually it's the brown trout when you think about that though, right? And like somebody that I actually know a guy who caught a brown trout and it literally had probably like a 6 inch brown trout still like the tail still hanging out of its mouth, and it ate somebody else's fly, like just kept trying to eat. And they're definitely voracious feeders and quite a species. So I think we're getting pretty close to 9 o'clock. I want to maybe wrap this up. I will certainly say I appreciate you coming on. I appreciate you sharing what you've done so far. I think when you've got if you do like publish the paper, we would certainly be interested in seeing that, or however you end up presenting this to the public, we would certainly be interested in that. And there are some amazing findings that come out of this, and you want to come back and fill us in on where you think it's going. I think we'd love to have you back and hear about it. So, but we certainly appreciate you taking the time tonight and share with us what you're up to, because I think it's pretty cool.
Yeah, thanks everybody for having me and sticking around to listen.
Awesome. All right, well, thanks again, Brandon. Thanks everyone for joining us. This is another episode of Talking Trout. I'll apologize to all the YouTubers out there who are looking for an actual video of a trout talking. This is not it. So with that, we'll say good night, and we'll see you next month. Thanks, everybody.
Thank you.